Welcome to another video on chemistry, specifically looking at the chemistry of HSC New South Wales, and we're going to be checking out the oxygen versus ozone. Now, a lot of the concepts, of course, that I talk about in here can be related across the world, but we're going to be looking at the chemistry between oxygen and ozone, the two allotropes of oxygen. Now, the thing is that when we need to understand this, the fundamental basis when you want to understand the chemistry of something is drawing its structure. So we've previously done a video on drawing the structure of those two, the Lewis dot structures. So let's draw them out. So let's do oxygen over here. Okay, so there's oxygen. And so let's look at its structure. The thing to look at here is that it is a linear molecule. So when it's linear, it means that any charge distribution gets cancelled. Now, if we think about it, oxygen has the same electronegativity as each other, and so therefore the electrons are distributed equally over that bond, and so you can say that they cancel each other out. Okay, so the type of bonds we're talking about here, or I should say the type of forces we're talking about, is something called dispersion forces. So if we were to look at the bonding, it's going to be dispersion forces. And if you remember, a dispersion force is one that is transient. In other words, it's not always there. So the electrons are moving around the oxygen atom and of course around the double bond and holding them together, etc. But at any one moment there can be a slight unequal distribution of electrons, and so they might be spending a little bit more time around this side of the oxygen just momentarily, and that gives them a slight delta charge, and then around here, because they're spending more time over on the left hand side here, this can have a slight positive charge, but that's only transient. It only happens very, very quickly, and then they disappear, okay, because the electrons are moving around. And of course you can have the reverse happening, where we have a delta minus over here and a delta positive over here. So dispersion forces are a temporary force. So they're a transient force, okay, and temporary, so they're very, very weak, okay. What about ozone? Well, let's draw the structure of ozone. So ozone we have, and we learned how to draw that structure in a previous video, and we said in that video that this was one form of a Lewis dot structure. We could draw the double bond on this side and the single bond on that side, and since there was two possibilities of drawing a Lewis dot structure, we call that resonance. And we said that this bond here was a coordinate covalent bond in that particular video. So if you're not sure about that, go watch that video. But this here is a bent molecule. So it's bent, right? The orientation around this central oxygen here is like a bent sort of shape, which means that charge distribution that we now have forms a dipole. It's a permanent dipole, but there's also dispersion forces. So there's two there. So that means that the bonding is stronger. The intermolecular bonding in ozone is stronger compared to oxygen. Well, what does that mean? Well, it means that it has a higher boiling point. So oxygen's boiling point is minus 186 degrees Celsius, and ozone is minus 111 degrees Celsius. So it's got a higher boiling point compared to oxygen. What else does it mean? Well, if we were to look in terms of density, then this is the same as air, because it is a composition of air, right? I mean, even though air is 78% nitrogen and 21% oxygen, the density is very similar to air, whereas this is more dense than air. Why is it more dense than air? Well, because of the stronger dispersion forces, they are closer together in terms of volume, and so the density is higher. We're going to run out of room here, but we'll see if we can write it over here. And if we turn of solubility, well, this is sparingly soluble. In other words, it does dissolve in water, in polar solvents, but not very well. I mean, it is a non-polar molecule because it's got only dispersion forces there. It does dissolve in water because obviously when you think about it, oxygen has to dissolve in water because that's what fish and other aquatic organisms need for respiration. So there is oxygen in the water, but it's not a very high solubility. And so we can say it may be sparingly soluble. Over here, it is more soluble, and that's because it has greater intermolecular forces there, the dipole. Let's just take this section over here. Of course, if you're writing it, you just continue down the page. We're talking about stability. Well, oxygen is stable Okay, it's a very, very stable structure, whereas ozone is unstable. So this resonating hybrid bonding that you could call here is not as stable as this double bond, right? Less energy is needed to break these bonds, and therefore it's more reactive and more stable, right? So it's more reactive. And therefore it's a greater oxidizing molecule. I mean, oxygen oxidizes things. The greatest example of oxidization is, of course, the formation of rust. But you also have biological oxidation, the oxidation of fats, the breaking down of fats. And so that happens with oxygen. However, ozone is even more reactive, and so therefore it's a greater oxidizing agent. All right? And so I guess we could put that last one there as oxidizing agent. Right? And so ozone is used as an oxidizer, and when it comes to water quality, we can pass oxygen through water samples to actually oxidize and kill any microbes in the water. Ozone is used in that type of in the purification of water process, so it is very strong oxidizing agent. So that's a quick comparison between oxygen and ozone. Hope that makes sense to you. You've got it all down, and we'll skip on to another video where we look even further at the comparison of maybe oxygen to a free radical. See you in that video.